In this problem, there's a grid that goes up to 500 on both axes. There's also a series of points that are plotted inside this grid. As for the queries, we are given a list of circles with the center coordinates and radius both stated. Our task is to, for each circle, determine how many points are inside of it. Points that lie on the edge of the circle are also considered inside the circle. Another important note to keep in mind is that all the coordinates and radii are given in positive whole number values. One solution is to simply loop through each point and calculate the distance from the center of the circle. This can be done with the distance formula. Then, if the distance is less than the radius of the circle, we can confirm that the point lies on the circle or inside of it. In programming, square roots are a complex operation that take a considerable amount of time, so to speed up computing time, we can square both sides of this inequality. Using this method, we loop through each point for every query. The time taken to compute each test case would then be the number of points multiplied by the number of queries. But what if we had more points, like some number close to 100,000? If this happens, then our time complexity would not be reasonable enough or small enough to solve the problem. Before I explain the other approach to this problem, I'd like to first explain the concept of prefix sums. A simple prefix sum is best described in a 1D context. Let's say that we have an array of numbers and we wanted to find the sum of all the numbers within some specific range. If this were the only task, then there would be no faster way to do it than just looping through all the numbers and keeping a running total. However, in cases where we need to find the sum of multiple ranges, looping through each range one by one would be too expensive. A prefix sum helps us pre-calculate all these ranges and solves each query in a single operation. As an example, let's take an array of 10 numbers. Now, in a prefix sum, the value at any position is the sum of all the elements before it plus the value at the current position. In our case, our prefix sum would be the following. In other words, if we wanted to find the sum of elements in the range 0 to 10, we can do so in a single lookup. You might be wondering how to compute the sum of ranges where the first element is not 0. This can be done with subtraction. Say we wanted to find the sum of elements in the range 5 to 10. We can do this simply by using the range 0 to 10, and then subtract the range 0 to 4. Keep in mind that since 5 is included here, we do not subtract the range 0 to 5 as that would exclude it. Now, this yields 45, and you can pause the video to confirm it. Now, how does this idea of prefix sums connect to our problem? Well, instead of counting each point one by one, we can actually use prefix sums to calculate the amount of points that lie within a specific range. Since we're told that all points lie on integer values, they can easily be expressed as an array. Specifically, we can use a 2D array with each subarray representing a y value on the grid. Now, we can focus on one of these subarrays. Remember that this array translates to the actual y value on the grid. Here, we represent points as ones and empty spots as zeros. If we use the prefix sum, the resulting array would be this. Using the logic of prefix sums, we can count the number of points in a specific range using subtraction. For instance, if we wanted to find the number of points within this range, we can use our prefix sum to calculate it. Now, when we're given the points, we can pre-calculate each of the prefix sums and use them to our advantage. The way to do this is to split each circle into many horizontal rows, and then we can find the range of each line and use that as a prefix sum range. In this example, we can pre-calculate all the prefix sums, and then use this to our advantage. Then we loop through each y value of the circle and use that to find the number of points that lie within the actual circle. One question remains though, that is this approach really faster than the previous one? The answer is that it depends. In the first solution that uses brute force, the time complexity is mainly determined by the number of points we have. If there are 500 points, then the queries would take 500 computations each. But in a test case with 100,000 points, that would end up taking 100,000 computations per query. The second approach has a time complexity determined by the size of the grid. The more rows we have, the more prefix sums we need to calculate. If the grid is 500 by 500, then the time complexity is 500 squared. Additionally, the time complexity for each query is bounded by the size of the circle. The greater the radius, the more we have to split the circle into horizontal lines. To reach an ideal processing time then, we would have to determine the best method for each query. If the radius of the circle exceeds the number of points, then it would be better to run the first solution. Otherwise, the second solution would be faster. This sums up the explanation for problem 1828 on Leetcode. Keep in mind that the official website limits the number of points to 500 and the size of the grid to 500 by 500. Therefore, the brute force approach would work just as well as the second approach. However, the second approach would be more feasible if the number of points were greater. I hope this video was helpful in explaining the solution behind this problem. Thanks for watching.